Simple subprograms were present in the earliest programming languages. These are subprograms that do not support recursion. Because we do not support recursion, the implementation can be fairly simple. On the left, we have an example program written in C. Now, C does not use simple subprograms. C programs do support recursion. However, we're going to model this C program as if it were being implemented using a simple subprogram as follows. Because there is no recursion, this means that there can ever only be one instance of any subprogram active at a given time. This, therefore, means that all variables can be statically bound in advance. So what we see here are several storage locations for variables and other information associated with each subprogram. These individual chunks associated with sub1, sub2, and sub3 are known as activation records. An activation record is filled with information associated with a currently executing subprogram. Now, the code for each of these subprograms also exists in memory, but that occupies a different region than is occupied by these activation records. When this function call, sub136, is made from inside the main function, the 3 and the 6 fill in these spots in the activation record. Also, the return address is specified as the address inside the main function where this call is made from. Now, in reality, this code would be converted into machine code, and of course, that individual command would be a series of assembly instructions or machine instructions, and so the return address would be very precise. But for now, I'll simply put main there. And then when the code executes, we see that the purpose of that subprogram or function is to add these values together. And so we would compute a return value, 9, that would go here. And when the subprogram returns, the main function knows to look into that location to find the result that was produced by the subprogram call. However, sub1 is also called from inside the body of sub2. So in the main function, when sub2 with a parameter of 4.3 is called, we actually go through multiple activation records. So first, this 4.3 gets mapped to this parameter D. Now, inside the code, we see that the variable truncated, a local variable, takes on the value of this converted to an integer. So that becomes 4. Then there is a call to sub1. Specifically, the call sub1 has parameters of 4, the value of truncated, and then a hard-coded value of 5. So now those parameters fill in the 4 and the 5 in the activation record for sub1. Those values are added. Oh, also, I'll note that the return address here is sub2, or the specific line of code from sub2. Whereas in sub2's activation record, the return address will be a specific address inside the main function. So this is showing the purpose of this return address field, because we may not always return to the same place. So we add these values in the code for sub1. That computes a value of 9. Then we return to the location in sub2 where sub1 was called from. Now, you'll see that the value of sub1, the return value, gets stored in the variable result. So this value 9 gets stored here. Because sub1 is just returned, all of these values are no longer relevant. Now, they would probably be left alone as they are, simply waiting to be replaced by the next call, but we can think of them as being not legal to access at this point. Now, we have a value for result, and we're going to compute a return value, and that is going to be the original value d times this result 9. 4.3 times 9 is 38.7, and so sub2 would return to the place in main where it was called from, and this return value, 38.7, would be waiting for the main function to use it in that printf statement on the left. Simple subprograms are easy to implement because the storage bindings are static, and that makes things much less complicated. However, it does mean we have to reserve a bunch of space in advance, even if we're not going to use it very much, and it also means we can't do recursion. All modern languages support recursion, so this model of subprogram implementation is not used in modern languages. Rather, a stack-based implementation is used, as we'll see in the next video.